computer. Okay, now let me share the screen. Yes, and then let me move on to the notes for it. Hope you are able to see the screen here.
Yes, sir.
Good. So this is periodic. See, we have a continuous time signal. We are taking samples of that signal. Okay, and then we would like to establish the relationship between how how they are related in time domain as well as in the frequency domain. That is what is of interest for us. Okay, so in a way we are first creating from that a discrete time equivalent in the continuous time domain itself is what we are doing it. As one of you have rightly, I think Gautam has rightly questioned it, why not directly try to establish, why again doing this multiplication with the impulse time? That's a very good question. We have on one side the integration part overall xc of t, but on the other side here we have x of n. So one way you could think of is just retain what is important. Okay, so anyway, x of n, you could see here the relationship here. Okay, let me also keep, hope this is writing. Let me just maybe this. Okay, let me pick some pen here and then I'll keep it here. Okay, so you could see here, see what you are doing is at an interval of t you are taking, so x of n is equal to xc of nt. Okay, so all that you would require is around that place, the rest could become zero. How could you do that? What you are doing is you are first creating a discrete time equivalent in the continuous time domain itself. So how do you do that? You simply multiply it with an impulse time. Okay, so that it has values only at repeated multiples of t is what are the values. So that's your impulse time, delta of t minus nt. So you are multiplying a continuous time signal with an impulse time. What is the equivalent operation in the frequency domain? Multiplication with an impulse time is equivalent to, in frequency domain,
Convolution.
right, convolution with the impulse time. That's exactly, so that's exactly what you had here. So by the way, before that we are just writing the expression completely here. You are doing xc of t multiplied with s of t. You could take that inside, and then t minus nt has value at t equal to nt. So you had written here xc of nt into delta of t minus nt. Okay, and now what you are doing is excess of t, what you are getting the multiplication with impulse train, multiplied with s of t. The moment you move to the Fourier domain, multiplication is equivalent to convolution and with multiplication factor of 2 pi, right? And what does this, if I am convolving x of t with delta of t minus t naught, what will happen? I am convolving, let's say I have a signal x of t. I convolve it with delta of t minus t naught. Okay, I have a signal x of t convolving with delta of t minus t naught. What would happen to that? This will give me,
X of t minus t naught.
right, the, so if you convolve it a given signal with a shifted impulse, your signal gets shifted by the same value, right? This all you are, all of you know this all. So that's exactly what is happening now. Delta of t, here you had delta of t minus nt, correct? That's here, by the way, this all of you would have worked out in signals and systems course itself, that for delta of t, for the impulse train, okay, s of t, the, I'll just use a different color here, and so will not yeah, so this, you know it, right? If you have an impulse train signal, right, if you have an impulse train signal, Fourier transform would still be an impulse one. But now if they are far spaced, if you are increasing the distance there in the time domain, the distance would come closer here, and vice versa in the frequency domain. Impulse would give you an impulse, and then there will be a multiplication factor of 2 pi by t. Hope you all remember that. This is like continuous time Fourier transform of periodic signals. That's what you have done it in the last semester course. So that's exactly what is here. So for example, you have t in the numerator here. This you get 2 pi by t here gets multiplied. Well, I have taken k, but it's up to you. You could have written n as well. That's after all a parameter you are taking here. And this gets multiplied with 2 pi by t here, because anyway that calculation will have 1 by 2 pi. So that would eventually give you 2 pi by t here. Okay. So this is what you have s of j omega. So your shift is by value of k times 2 pi by t. Okay. And then we have seen that the time period at which you are sampling is t, you are calling it. Okay. So fs would be equal to, not this one, fs equal to 1 by t here. This placement of this is not convenient. Let me put it down. Okay. So that I could make use of this whenever. Okay, fs equal to 1 by t here. And then if I want to write it in terms of omega, it is 2 pi fs, that's equivalent to 2 pi by t. That's how you are getting that. Okay. And then this would, k times omega s would in fact, now when you are multiplying it, with that convolution, this gets shifted by k times omega s. But then you see here, there is a summation. This convolution is not a single convolution you are doing it. You had a summation, and then suppose there is n value here, then n vary from minus infinity to plus infinity. So you have now n copies, each copy placed at a 1 at t naught, 2 t naught, 3 t naught. Okay, on the negative side, minus t naught, minus 2 t naught, minus 3 t naught, and so on. Right? That's exactly what is happening here. And then this 2 pi by t is coming from the Fourier transform of the impulse train. And then this multiplication converted to convolution will give you 1 by t. So with that, you will be left with 1 by t here. Okay. So to put it simply now, suppose whenever you have a signal, okay, that moment you are multiplying with an impulse train, this multiplication is equivalent to a convolution in the frequency domain. So the moment you are convolving with impulse train, each impulse in that impulse train will make one copy sit there. Okay. And now this impulse train is having a delayed impulses with multiples of t. So at every multiple of t, you are keeping one copy. That's how the excess of j omega is there. Now, notice here, this omega s is nothing but 2 pi by t. So when you are placing these copies, if this omega s is small, okay, in other words, you are taking samples very far. Okay, if that is the case, then what would happen? There will be no overlap between the frequency spectrums, right? So that's what you would see here. So omega s is 2 pi by t, correct? So if you are taking samples very far, then that is when there is an overlap between the frequency spectrum. So that's what would happen, and that's referred to Eliassen here. So to avoid that, what should happen? So this is a very important theorem in communications. You will come back to it, and probably you would be discussing in even more detail here. So these signals, whichever we are considering, are called as band limited signals, because here you could say this is the upper limit and this is the lower limit for the frequencies, beyond which the frequency magnitudes of frequencies are zero. So that is given by your omega n, and of course that signal being real, you will have the symmetric one on the other side, minus omega n. So here you could see here, this length is omega n. Similarly, this length is omega n, and this value being omega s, this would be equal to omega s minus omega n. So to avoid any overlap, what should happen? This omega s minus omega n should be greater than omega n. So that's what we have seen here. So that's equivalent to omega s being greater than or equal to 2 times omega n. So if you just look at whether you could recover the original spectrum of it from a continuous time signal which is multiplied by impulse time, this is a very interesting thing. If your signal, so the assumption is your signal is band limited. If your signal is band limited and you have selected your samples with a spacing t in such a way that the omega s is twice the omega n, which is the highest frequency you have, then you could perfectly get back your original continuous time domain signal even from the samples which are there in the continuous time. Is this part clear? This is in fact very interesting thing. You are just taking samples, but you could get back the original signal from those samples. Of course, we are still in the time domain, but this is equally applicable even when you move to the discrete time domain. But since we right now have seen just 2 steps here, hope this point is clear to you already. So you have a continuous time signal. You are taking samples of it at t. If this t is in such a way that 2 pi by t is at least twice the maximum frequency that is there in the Fourier continuous time Fourier transform of that signal, then all you need to do here is you just need to apply a low pass filtering here, okay, and with a multiplication factor of t, this low pass factoring, and then you will again get back this exactly the xc of j omega. You could get it. Once you have xc of j omega, you take inverse continuous time Fourier transform. That should give you xs of t. So in other words, even if I have only samples, I simply would be computing the continuous time Fourier transform, then apply a low pass filter. Since there is magnitude of frequencies is varying by a value of t, I will just use here t multiplication factor there. This would be from so the threshold will be such that it is in between this omega n and omega s minus omega n. That's good enough. I will get back the frequency spectrum of the continuous time Fourier transform. I take inverse Fourier transform, I'll get back my signal. Is this concept clear to you? Are there any questions here? This is a very, very important result, which is telling you that all you need to guarantee here is your signal is band limited and what is the highest frequency of that band limited signal. That's all. Then you could tell with what rate you need to sample the signal, through which by retaining only those values, you could anytime reconstruct back your original signal. That's the nice thing about this. Is that clear? So that rate at which you need to sample is given by, this is called as an Nyquist theorem, okay, which as long as your 2 pi by t is greater than or equal to 2 times omega n, you could do it. Or if you want it in terms of the t, as long as t is less than or equal to pi by omega n. So if you tell me the highest frequency you have, if your t, as long as your t is smaller than or equal to pi by omega n, it's guaranteed that I could always get back the continuous time Fourier spectrum of the original signal out of which I have taken samples. Okay. So if this is clear, I'll move on to the next video lecture. So this is what we have discussed in the first video lecture. So if some of you haven't gone through it thoroughly, please do go through it. This would have a nice, this I would say the most important topic which you would later find out application in various domains. Okay, be it communication systems, which is a subject, or be it even in image processing subject, or be it in medical imaging subject. This is the core for even MR medical imaging. One has to understand the sampling has to be absolutely clear. Or there are many other places where the sampling play, or computer vision as well, because the moment you are doing anything in the frequency domain, this is something, and the moment you are taking samples, okay, you are downsampling or upsampling it, this is a very core of it. Okay, so I guess since there are no questions, I guess that this is clear, absolutely clear to everyone. If that is not the case, you just ask it. Right? Yeah.
What's the difference between xs of t and x of n?
Xs of
t and x of n, x square of n.
xs of t, and so this one you are saying one is xs of t and another is x of n. That right? This is your, what is the difference between these two things, correct?
Yes, sir.
Yes, good. So can anyone try to answer this question?
Sir, excess of t is just after multiplying it with del of t, that is
Right.
continuous time impulse has a little value in and around zero as well as having a value at zero.
Correct.
So it carries on that nature, not
Right.
completely discrete, but kind of discrete.
Very good. So that's one key thing where excess of t is this being delta. See, again, nobody does it this way in practice because delta of t and other things are not realizable. But at least mathematically, you could say that infinitesimally small region around your t equal to any integer multiple of capital T, you have a value there. Okay, that's one aspect. There is that's one thing that is not there in x of n. But if you look at in terms of the Fourier domain representation of it, can you tell me another important difference between the both? That's one correct point. There is one more important distinction that is happening the moment you are moving from xs of t to x of n. Hmm?
The concept of time between multiple impulses is gone.
Correct. You are right. So let me slightly rephrase it. Your x-axis is the normalization happening in the x-axis is varying. See, when I have t here, for example, I have them at 0, t, 2t, and so on, even for excess of t. But the moment I have n here, this information of t is dropped. So all you have is 0, 1, 2, 3, and so on. Right? So your x-axis normalization is varying. That is why if you, those of you who had already gone through the next lecture, you would get this relationship of capital times omega t equal to small omega. So if I give you, for example, xs of j omega, and on the other side x of e power j omega, so how do you get the relationship? X of e power j omega, okay, would be equivalent to, in fact, s of j omega computed at omega equal to small omega by t. So see, there is a scaling happening on the x-axis, if you want to put it that way. That scaling would now is something responsible to bring it from minus infinity to plus infinity, whichever is there. All frequencies are there. Those will be now get mapped one band. Yeah, you will get now omega s. Earlier is 2 pi by t. Your omega s is equal to 2 pi by t. So you are keeping the copies. If I give you t, you can tell me where the copy is kept, multiples of omega s, right? Omega s, 2 omega s, 3 omega s, and so on. And now when it comes to the omega now, because of this normalization happening, earlier the values are there at 0, t, 2t, 3t, 4t, and so on, capital T I'm talking about. But the moment you make them into 0, 1, 2, 3, as I mentioned here, capital omega, small omega will be equal to omega times t, which would give you 2 pi, for example. So the copies, you know for sure that now they are kept at 2 pi, 4 pi, 6 pi, and minus 2 pi, minus 4 pi, minus 6 pi, and so on. And this being periodic in the interval of minus pi to pi. That's so, in other words, the normalization happening in the x-axis, okay, of course, that is capital omega is there here. This is excess of j omega and small omega. So that's when you are making a shift from there to here. This is the second thing that is happening. Is it clear? So first thing, I think one of you had mentioned it. What is happening there is you don't exactly will have only at, by the way, this part he already Oppenheim and Scheffer, you will find it slightly different way, but this is a more precise presentation. He directly considers that as no integration is required, as if the diagram and the math would be given. But I find this is a bit more precise way of presenting things. Okay. There is some time coming. Maybe keep your mic in mute. Yeah, you could again please switch it on as and when you want to ask something. Okay. So is that clear? So then, if there are no questions here, let's move on to the second. Well, there is just, let me myself keep it in mute. There is Harshavardhan's one is giving sound. Yeah, Harshavardhan, I am keeping it in mute, and as and when you want to ask something, you keep it, you unmute it, please. Okay. Yeah. So somebody has asked in chat, sir, can you turn off your camera because my internal speed is not, okay, yeah, sure. That's better actually. I'll turn off my camera so that hopefully you could be able to see the things better. Okay, that's a good suggestion. Yeah, we'll do that. Okay, let's go back again. Let me share the screen and go back to this notes again. Right. So this is where we are writing the Fourier. Yeah, this is exactly what we discussed right now on how this excess of g omega, x of e power j omega, and this xs of j omega are related. Okay, this is exactly what has been done here, and then you would see this is the relationship x of e power j omega. Yeah, you would see that this is the first relationship, excess of j omega. So here first we would try to express excess of j omega and xc of t. That's the first exercise we are doing here. Okay, this is the relationship we are going to establish here. So what did we do there? We know this is very simple. This, in fact, we did most of the things in the previous. So the way we are trying to write is, you write the expression for excess of g omega is minus infinity to plus infinity, is simply the definition of your CTFT, right? Now xs of t we already know from the previous thing. So this is nothing but, and you are multiplying it with an impulse train and has values only at delta of t minus at multiples of 2 pi. So instead of the integration, you could simply write the summation. This we have done in the previous presentation. So this is what you got it there. Okay, this is what you would be getting there. And after that, so that's what has been substituted here. You are varying t now. Well, this delta of t minus nt is non-zero and equal to 1 only when t equal to nt, although you are integrating it from minus infinity to plus infinity. So what you could do here, simply there is any summation here. In the summation at t equal to nt's you have values, so you simply remove this minus infinity to plus infinity, and this t you replace with nt, sorry, this t, that anyway this, of course this also you would replace, but that is when this is equal to 1 delta value. So this t you replace with nt here, right? So then what do you get? Xs of j omega is equal to summation n varying from minus infinity to plus infinity x of n into e power minus j omega t n. Okay, now you compare with the definition of x of e power j omega. See, this is again a simple definition of DTFT is what you are writing here. And now you compare both of these two things. What you could see now is, if all that they vary is, here there is capital small omega and here capital omega t. So x of e power j omega, in fact, you could get from xs of j omega by substituting this omega equal to small omega by t. That's all. Okay. So that gives you the relationship between the DTFT of your discrete time signal and your continuous time signal after multiplying it with impulse time. So that's what has been done here. And then XC of, well, now here, this is something we have already done in the last lecture. Okay, or the last note we have done it. So you had 1 by t multiplication here, and then shifting by omega s or 2 pi by t here is there. So that's giving you excess of j omega in terms of xc of j omega. So you had multiple copies, each copy placed at integer multiples of omega s, and then there is a scaling by 1 by t. Okay, so this now x of e power j omega in terms of xs of j omega is what you have just now done, right? This is, you know it. So from here you could, so all you need to do is you substitute omega equals to small omega by t in this expression. That would give you the value of x of e power j omega. So you could see here x of e power j omega equal to 1 by t xc of j times omega by t minus k times 2 pi by t. So that's all. So the moment you are moving, you have a continuous time signal, you are moving to it's a discrete counterpart of it. What's happening is, depending on at which value of omega s you are taking the samples, the samples at which you are taking the distance t, okay, the rate at which you are taking samples will tell you where the copies will be placed. So there will be multiple copies. The moment you are sampling, it brings multiple copies. Okay. So what you have now is omega s, 2 omega s, 3 omega s, and also on the negative side you have copies of it placed. And then you could see here small omega by t. Okay, because there the t information is lost and you have only 1, 2, 3, 4. So the scaling along x-axis would give you here omega by t. And anyway, multiplication with an impulse train, okay, and then convolution, you will have additionally 1 by t. That's all. So these three are the effects: multiple copies placed, each copy placed at omega s, and then magnitude getting scaled by 1 by t, right? And that's all. So these are the three effects. So this is what you could see here. The first one is assume, again, we considered it as 1, but you could consider anything here. For example, some value m. All that would happen is here you will get m by t. That's all. It's just a scaling of the magnitudes will be still 1 by t. So doesn't matter. Okay. So what you did is assume that you have a band limited signal having frequencies minus omega and 2 omega. And again, I'm drawing triangle for convenience, but there is nothing wrong. If I could have drawn anything, or in like for example, I could have drawn minus omega and 2 plus omega in this way, or even anything is fine. It could be anything. All that we need to know here is what's the highest frequency that you have with non-zero magnitude. Okay. So then after that, xc of j omega you are plotting here. With that, this 1 has become 1 by t. Now the next copy, this exact, other than that, in the x-axis there is no variation. Now the same copy identically has been placed at omega s, 2 omega s, and so on. This omega s is equal to 2 pi by t. That t is the rate at which you are sampling. The smaller the value of t, the farther the copies are kept, so that there will not be any overlap. Okay. And then moving from excess of j omega to here, additionally, all that it changes is this 1 by t would remain same. Okay. And this is the relationship omega and omega, capital omega times capital T equal to small omega. So small omega is omega by t. Okay. So this we have written omega as equal to 2 pi by t. So multiple omega. So that corresponding value when you come to omega here, that would be multiplication with the t. So that would give you 2 pi here. So doesn't now where the copy is kept doesn't really depend now on when it comes to DTFT, because that normalization has been done. So everything is scaled now along the x-axis. Okay. This omega n also would now come at minus omega n t. But see, this is uniformly scaled across the x-axis. So the proportion of either overlap or the proportion of distance with respect to the bandwidth of the signal would remain same anyway. Okay. And then this is the case when there is an overlap. Okay. Notice here, when there is an overlap, there is no way you could get back exactly this part, right? Because once they overlap, you don't really know. This is corrupted essentially. So you won't be able to get back those in those regions, the magnitudes of those frequencies you won't be able to get. So this is the case of aliasing. But as we have discussed, as long as your omega s, okay, is greater than or equal to 2 times omega n, there will not be any overlap. So if it is exactly equal to 2 times omega n, then there will be, so something like this. Okay, exactly it will be there. But still you could take the low pass filtering here. That should again should let you to get back to what is there. So that's all for the first 2 classes. Let me come back here. So let me just go back to the poll. Yeah, very few have gone to the third and fourth lectures. In fact, there are still few who are yet to go through even the first lecture. So I would strongly recommend you to again finish them off. Okay, 24 out of 30 have, yeah, all of you have posted this. Okay, so please go through the third and fourth because if I discuss it, this you please spend some time on it. You now that you know more or less the flow on how we are deriving the relationships, you start from scratch in your book, in your notebook by yourself, and do that out and then cross check it. These concepts have to be absolutely clear for you to understand the latter things. Okay, so then probably the next thing. Okay, so yeah, I could in fact, yeah, I think, yeah, 53% of people have gone to the first result. Okay, yeah, you could see the results also right now, I think, right? This poll results also, is it visible to you? I
Yes.
hope. Yeah, good. So yeah, I would rather say, yeah, please, only one, two, almost 50% of people are yet to go through the remaining things. So please go through it. And then I think, so one more thing, I'd like to stop this thing. Yeah, let me now, I think, share this out. Okay, so yeah, one more thing is whether to have one class or two classes, a Zoom session. um, I would feel maybe four if I ask you to see roughly two video lectures is equivalent to one class in a way. Because I'm trying to keep it to 30 to 40 minutes only each class, so that otherwise if the video is too large also, that creeps within us some inertia to go through it and it becomes a bit boring. So I'm trying to modularize it as much as possible. So one way is and that too you would be then seeing it only once in a week we would be seeing. So I would say we can keep our discussions short, like just like 45 minutes and all here, but rather have two sessions, every session two videos. That's one possibility. So let me put one more poll here. So personally I would go for that. Say for example, today we discussed first two videos. Next, let's say Tuesday, Wednesday around 10:30, or we could figure out convenient time for you guys also. Okay, this let me put one more poll here. Number of Zoom sessions. Okay, I would personally prefer having two sessions a week. We could keep them small, like not necessarily 1.5 hours and all. Even 45 minutes to 50 minutes would be good. So that's what I feel. But let us see what you feel, and then let's take a call. Yeah, so that you will be, yeah, we don't know how things turn out over the period. So better we also, I would personally feel as much as we could cover, that's better we are done with it, so that if we are done early than other courses, then we will just simply stop. It's not like we will try to cover more. Okay, so yeah, please let me know your polling there. Is your CR there today? Yes.
Yes, sir, I'm here.
Okay, good. So what happened to the rest? Almost 15 students are missing today.
I'm not sure, sir.
Okay.
Like I updated everyone that there is a session today.
Okay. So I would request you actually to do me one help. You have hopefully a WhatsApp group. So those who are missing, so please let me know what is their concern.
Sure, sir. Like just share me the attendance list of today. I'll put
Yeah,
the
sure. So
message into the...
yeah, I would Vaishnavi, hope you are taking the attendance. Yeah?
Yes, sir. I have taken, sir.
Okay.
I'll send.
Yeah, please send it to Yashas, and please, if possible, please get back to me by the end of day, Yashas, so so
Sure,
if
sir.
there are any genuine concerns which we could address, let's do that.
Sure, sir.
Hmm.
I'll message you.
Yeah, this, as I mentioned, in my opinion, let's keep it short only. This Zoom sessions will be some 45 minutes is good enough. This way, if you come prepared for it, that's what I feel. But let's see. But 19 of 30 have voted so far. So let the rest 10 also vote for it. If it is in the border, then I will take a car. So meanwhile, if you have any questions of what we discussed so far, we could quickly go through them.
Excuse me, sir.
Yeah.
There was one question that I have.
Ah.
Is it necessary to take a band limit?
Is it necessary to take a band limited signal? Right? Very good question.
Yes.
Whatever we are all discussing so far is applicable to a band limited signal only. You won't be able to say, unless it is a band limited signal, you won't be able to say what is the good enough sampling rate. I won't be able to say. That's one thing. Nevertheless, what is usually done in practice is, you might not be all the time having band limited signal, but sometimes it is absolutely fine to drop the higher frequencies, ignore the higher frequencies beyond a particular value. So usually the signal will be passed through a low pass filter. Low pass filtering is done, and on that is treated as your xc of t instead of the original signal. Let's say x of t is there, your original signal, which not necessarily a band limited signal. So what you would do is, you do a low pass filtering and then you follow that. See, unless you don't know the extremes of your frequencies, you won't be knowing where to keep, at what rate you need to sample in order to avoid aliasing, and then finally get back to your original shape, isn't it? So one way is, if your signal is being band limited, is very good. Otherwise, see, while you are constructing back the signal with all these frequencies put together, you would take a call on what is good enough frequencies, and beyond that you will make them all zero. And that's how you make the signal band limited if it is not band limited. Does that answer the question?
Yes.
Okay, good. Again, there will be other slightly varying things also. Suppose if the signal is a band pass signal, hopefully we will try to give such questions, 1 or 2 questions in your exercise. This, you could stretch this sampling rate. In fact, if you're this, you will definitely come across in your communication course, where you will have a band pass signal. So then this is not omega. Now the rate at which you sample, omega s frequency, should be twice the omega n. But if you have a band pass signal, okay, so band pass signal, if you have it, you could do even much better than this. So see, the idea is, with how many less number of samples will you be able to get back your original thing, okay? Because your processing burden, computational complexity of that, everything comes down, particularly when you are dealing with it at a large scale, lot of signal of long duration, if you are dealing with it, or if your algorithm is a complex algorithm having order of your exponential order of number of samples, something of that nature is there, then you would rather prefer to have as many less number of samples as possible. So you would see, this is what we discussed in about the band limited signal. But if you have a band pass signal that could go beyond, means even at larger values of t, that results in means omega s here should be greater than or equal to 2 omega n. That limit also you could stretch there. Okay, it did not necessarily be twice the omega n. Could go even you can come little bit lesser than that as well. Again, depending on the width of your band pass signal. But this is the very generic thing. If you don't know anything about the signal, you simply pass it through a low pass filter, make it band limited, okay, and then omega n. Now, yeah, usually people take 4 times omega n, is also not very uncommon. For example, what is the range of frequencies that our ear could distinguish or even listen?
20 to 20.
Right, 20 kilohertz. So what should be, so that you could think of as a band limited signal having a frequency of, so this what you are talking about is fn, right? In hertz it is there. So if you multiply it with 2 pi, so that would be equivalent to uh, uh, 40 pi. That's your omega n, correct? So in fact, it's not uncommon you take 4 times of omega n in practice to avoid any other, there will be few more practical issues also. That's what they do it. So this tells you that even if you have a signal, for example, you recorded which could record frequencies beyond this, then also you do a band pass filtering kind of stuff. Yeah, any other question?
Excuse me, sir.
Yes.
How do we find the Fourier transform of that impulse train?
Okay, so just I would say you go back to the signals and systems you have done there. You refer to this. Even if you have the Oppenheim book, Oppenheim and Wilsky textbook, please go to the continuous time Fourier transform of periodic signals. Okay, that's where you would be dealing with it. I could go through it now, but I would leave it to you. You just refer to that continuous time Fourier transform of periodic signals. So this is essentially a periodic signal. Once you do it, you again get a periodic signal there with the spacing changed. Now it is, if it is t, you get here 2 pi by t, and then there is a scaling factor coming. So if that is not, so I guess CTF-TF periodic signals, is it covered last time? Yeah, I guess this should have been done. I think this might have been already done in that course. If not, we will then go through it. No, did anyone remember doing this periodic signals, finding out the continue? You will initially start with Fourier series of periodic signals. Then you will go to Fourier transform of aperiodic signals. Then you will come to Fourier transform of periodic signals again. If that is not covered, then I will cover it in the next, maybe next meeting I will cover. Is it covered?
No, sir.
No? No?
No, sir.
No, okay. So no one remembers that this has been covered? Nobody feels that this is covered?
Like I'm referring my notes, I don't see it.
Okay, okay. So then I will, yeah, this is a slightly tricky thing. We will do it probably then in the next session. I'll do that now then. So you please meanwhile go through it. This, yeah, it has to be done slightly differently than the usual way of doing it. So if that is not covered, we will do it actually. In the next meeting, we will do it. So still 13 people have to decide. So I should have given the other option that anything is fine, or nota they will call, none of the above, which I could then take it in my favor. So 20 of 33 have, yeah, I would say you give your voting there so that we could see what to do there. By the way, if I take 2 classes, does it hurt you with the bandwidth and then attending to the other classes? So basically, the idea is I would, so maybe 3, 4. So far I made 3 video lectures. I mean, the 4th one is actually 3A, 3B, I call it. So 4 more video lectures and sampling would complete that. And after that, I would move to DFT. Maybe 2 weeks on DFT should be fine. And after that, I would take maybe 2 class, like 1 more class. That means 2 video lecture perhaps on FFT. So with FFT, I will wrap it up. So I will not go to any filter design as of now, given situation. So let's see. So I would say let others also vote. Are you able to vote from your mobiles also?
Yes, sir.
Okay, okay. Yeah, then please make use of your your voting rights. Okay, yeah. Meanwhile, if you have any other questions also, you can please ask me. Since not many of you have gone through already the last 2 video lectures, I am not going through it right now because it doesn't make. So if I quickly try to cover the same before you go through it itself, that will bring more confusion than clarity. So I would prefer waiting for the next lecture. Okay, at least some 60 to 70% of people have gone through it, then it is fine. So yeah, please do that out as well. Okay. Yeah, I think a lot of people have most people have no opinion here. So mm, yeah, I think then I would, at least for this week, then we will go yeah, this is right now 50-50, and others, I think those who have not voted, I think they prefer whatever I decide. I assume that. Okay, so what we will do is, at least for the this week, we will have one more session. Okay, this would actually wrap it up till whatever I have uploaded so far on sampling. Okay, so we will finish those two reconstruction of the signal. Now the next lecture would be, given your x of n, how could you get back xc of t? Okay, so what all would happen there? That would be discussed in the third lecture. Fourth lecture is simply an example. That's all. I worked out one example there and gave you a couple of exercises there to work out. Okay, so you please do that. And let me see when the calendar is free. It appears Wednesday 10:25 slot is free. 10:30 same slot. I think most of you would prefer at 10:30 rather than at 9, right?
Sir,
Sorry?
hello? Sir,
Yeah.
sir, actually, in like from 10:30 to 11:30, Vignesh sir is planning to take the
On
class.
Wednesday, yeah?
Yeah, on Wednesday.
Okay. Are you fine with afternoon session also? See, 9 to 10:15, I have no problem. One class I could do it. For me, it's fine. But if many of you could not attend it, it doesn't solve any purpose as such, right? So let me pause this recording anyway. I think